Welcome to Machine Tool Maniacs, the podcast where machining, fabrication, entrepreneurship, and bringing ideas to life collide. Around here, every story is a success story. I'm Matt, a second-generation manufacturer who's been in the shop since I was in diapers, learning the tools, the trade, and the people behind it all. Nearly everything in our daily lives is passed through a CNC machine. And we're here to spotlight the makers, turning raw material into reality. Whether you're dreaming big or building bigger, this is your inside track to making it happen. Welcome back to the podcast. I am joined today again with Will, and we are here to continue our machine talk series that we do. We started, before the end of the year, we started a series breaking down the major components on CNC machines. So today, the topic is the mechanicals of your CNC machine. So the first episode we did was the foundation. So we discussed casting types. We discussed what the base layout of your machine. And this episode is going to be about the mechanical components that are on your machine. Say hi to everybody, Will.
Hi, everybody. It was between that or saying moshi moshi, but most of our listeners probably wouldn't even know what that means. So
Well, that's Japanese, isn't it?
exactly, it's how they answer the telephone.
See, it's very fitting because a lot
Well,
of mechanical stuff is made by the Japanese.
oh, absolutely.
So give us an intro, Will, of what the mechanicals of a machine is that we're going to be covering in this episode.
So we've already covered the foundation, like you said, and so now we're getting into some of the things like your motion control. So whether it's boxways or linear guides, or even hydrostatic ways like the kerns. So we're going to talk a little bit about that. We're going to talk about ball screws.
What to
Yep,
look for in a quality machine,
yep,
where some builders will make sacrifices and where some builders go above and beyond, and that's
yep.
usually reflected in the price of the machine.
Absolutely. Kind of getting into that. It's an extension of our foundation. If you spend all this time and effort designing a really good, solid, strong foundation and with a high amount of uh, both static rigidity as well as good performance on dynamic rigidity and really our motion system, the motion systems and things can also affect that dynamic rigidity. By going over our mechanical stuff, we're just adding another layer or peeling back another layer of that onion
Mm-hmm.
of that is machine tools, and they all kind of build on each other and support each other in different ways to make it to where the final product is able to create the masterpieces, as it were, that machinists create on them.
So you brought up, what did you say? You said static versus.
Static and dynamic rigidity.
Explain that to us. I don't. I'm not even really familiar with that.
So your static rigidity of a machine is how well it handles a consistent amount of force being applied to it and the amount of deformation or change that the machine has. So a good example of that is a constant force would be the weight of a part that you put on the machine's table. Okay.
Okay.
So that you put, say you've got a C-frame machine like a Haas VF4 and you put a 1,500 pound billet on there to machine a part. That 1,500 pounds is going to affect the machine. It's going to concentrate weight, and it will cause a shift in either how the machine frame is sitting. Like I don't want to say bow, because when people think of something being bowed, they think, oh, it's turning into a potato chip or something. We like when you're machining really thin material, but you have to hog a lot of material off of one side and then how it wants to cup up or cup down. That's
Hmm.
what people think of. And if your machine has a good rigid, statically rigid frame, that deformation of a 1,500 pound part sitting on there could only be a few tenths. But if you got kind of a crappy design, it could be a couple of thousands.
Yeah.
But that's what like your static rigidity of a machine tool is, right?
Okay.
So then your dynamic rigidity of the machine is how the machine handles changing loads and vibration. And so that's when the part is potentially moving around, how it handles that, how it handles the forces that are applied to the machine frame when you go into the cut versus coming out of the cut, and how hard and how fast you're pushing that tool through the material, plus the potential vibration of the different cutters, because you're going to get different vibration from, say, a 9 flute cutter versus a 3 flute cutter or a 4 flute cutter in the same material. It's going to create a different harmonic. And so your static rigidity, or I mean, excuse me, your dynamic rigidity of the machine is how well it handles the vibration, the changing load, and everything like that, and what effect that has on the outcome of the part for accuracy, surface finish, etc.
So moving into our first layer of motion control systems,
Mm-hmm.
we are going to talk about your machine's ways.
Yep.
So, and I'm sure everybody that's in this field has heard the term of a way. So, some machines have linear guideways and some machines have boxways. Let's elaborate on boxways to start out with.
So boxways was kind of we could call that the granddaddy of machine construction. And essentially, what that was you'd have your casting, and on the on the main foundation for the y-axis, you would have a big, wide area that was ground or machined and ground, and you'd have this big square uh, slab, essentially of iron, and you'd have two of those that are spaced out from each other, and those would be the ways that the saddle or that the table's saddle would sit on and move back and forth in the y-axis on a standard C-frame machine.
Mhm.
And then on the bottom side of the saddle, you would have basically two U-shaped channels that would precisely fit down over those big wide slabs that are on the foundation or the base of the machine. And then you would pump oil into there to create a hydrostatic bearing, right? And so essentially that thin layer of oil would act as the primary bearing, and the saddle of the machine would float on that. That's just kind of the basics of it. Another one that you could look at that aren't boxways, but it gives you an idea of how a boxway would fit together, is you look at a Bridgeport and you've got dovetails, right? So you've got a male dovetail and a female dovetail that fit together, pretty relatively precisely. And then there's a gib or jib, however you pronounce that word, that's put in there that's kind of a precision made piece that's kind of tapered. And depending on how far you push it in or take it out, that tightens up or loosens how tightly those dovetails fit together. And you have the same kind of thing on boxways. Now, one of the advantages you have with boxways is for really heavy machining applications, like when you're getting in and just getting nasty with tough materials, big 50 taper beasts. Like that's when boxways really shine, because you have a large surface area that all of that force is getting dispersed over. And so it's able to dissipate the force and the vibration and things really, really well because you've got the mass and you've got the surface area to dissipate it well. Um, you can still buy brand new vertical machines, even like 40 taper machines that are box ways. Um, for mills, for lathes, you can still get lathes that are boxways, like the Okuma LB series. They're boxway machines,
Hmm.
and they are just tanks. Or the Doosan Pumas, the Mori NLXs.
Yep.
They're all boxway machines. Hell, it's even gotten to a point where Haas started importing a boxway machine from, I think, Taiwan or something, and put their sheet metal and their control and motors and stuff on it to be able to say, yeah, Haas has a boxway lathe now.
Yeah. I think it's definitely worth bringing up while we're on the conversation of box ways. You do sacrifice a little bit of speed
Oh,
compared
you
to
you
linear guideway.
depending on the builder, you can sacrifice a lot of speed. Though interestingly, uh, shout out to Kitamura on this one. Their boxway horizontals, like their HX 400,
Hmm.
that's still a boxway machine, and its rapid speeds and motion are as fast as a Makino. They're
Really?
moving at like 60 meters a minute, which for those of us that don't speak metric, that's 2,396 inches a minute.
Is that the little 30 taper one they make?
No, the little 30 taper one is actually on linear rails.
Okay.
But when we get into linear rails, well, we can talk a little more on it. But Kitamura on any of their machines that use linear rails, they oversize them. I
Hmm.
say oversize them. You they use large linear rails for the application. Is
Yeah.
is I guess is how I should say that to properly describe it. But yeah, the little 30 taper guy, he's on linear rails. The HX 300, which is a 40 taper machine, but 300 millimeter pallet, that's on linear rails. But the 400s and the 500s, from the 400 size horizontals and up, are all boxways on the kitties. So, and they're keeping up with their competitors like Makino, the A51NX, which is their 400 millimeter size machine. That's on linear rails.
It's definitely worth mentioning too, and I want you to elaborate on this for us, is scraping. So
Yes,
that boxways and machines that are built with this type of format. Now, like you said, Bridgeports also have kind of a form of a boxway, even though it's not really a box.
yep,
They have scraping on
yes,
them as well. So,
yep,
do you mind explaining to the audience what scraping is and how it is advantageous?
absolutely. And just so you know, uh, that getting into scraping is a part of machine tool building and precision that starts to tickle my tism just a little bit. Uh, I've actually been looking at attending scraping classes for
Yeah,
machine refurbishing this year because
nice.
there's a couple of guys that still offer those classes. I am looking up books and things, and I mean we're talking books that haven't been printed since like the 70s about this kind of stuff.
Hmm.
So what scraping is I first have to differentiate a couple things. You have scraping, and then you have what's called flaking. And they use the same tools, but they're different techniques. Flaking is used to accomplish two things. One is it's for a little more decorative flourish, but that's kind of a secondary reason. Flaking is primarily to create marks that are dug down into the surface, usually about a half a thou or a little more shallow, where oil gets trapped. But that acts as like a little bit of an oil reservoir to help keep lubrication between the two sliding surfaces of the box or dovetail way. Right? That makes sense?
Yes.
Okay. So now what scraping is uh, we can explain it like this. So you use the same tool as what you would use for flaking, which is usually it's a longer handle, and then on the end of it, it's got uh, for modern ones, it's a carbide tip that's been ground to very specific geometry. But prior to having good carbide or good sintered carbide pieces, it was also like high speed steel or tool steel, where it would be again made to very precise geometry. And so when you build a machine that would require scraping, like a boxway, it's usually the scraping is usually done on the uh, I guess you'd call it the pocket side. So you've got the box, again, going back to what I described earlier on the y-axis of a C-frame machine. You've got the big square or the big flat slabs on the foundation, and then you have the C-shaped cutouts on the bottom of the saddle that fit over it. So we'll call that C-shaped pocket, uh, or that C-shaped piece. We'll call that our pocket. And so the scraping is usually done on the pocket side in the case of ways, and that's because it's harder to get a really precise finish surface grinding inside of a pocket, whereas it's a little easier to get a really nice finish on the slab side of the boxway. Okay, so you come in, you'd harden the slab and then surface grind it. What happens is once the box is like, you can get the slab, the male side of the boxway machined really smooth, really flat, and it looks beautiful. And I mean it's for all intents and purposes that is a flat surface. But you can actually have a problem if you have two surfaces like that, like Joe blocks, gauge blocks. So the edges of gauge blocks are super flat, right? They're machined, they're ground, and then they are lapped. So they are both edges are incredibly flat and incredibly smooth. What can you do with gauge blocks
Ring them
when you
together.
can ring them together? That's not very good for a component that's supposed to be moving back and forth, is it?
Yeah, that's true.
And so what can happen is, even with that oil in there, because of the weight, if there's nowhere other than out of the way, uh, nope, sorry, that's out of the boxway, I should say. If there's nowhere else for the oil to go, the weight from the table and the saddle and the part and everything, if the machine stops for very long, it'll actually squeeze the oil out of there, and then you have a rung. You basically have a really heavy gauge block
Yeah.
problem where it's all rung together,
Yeah,
and
that's
so
right.
it's a bear. So scraping is used to not only make for a very incredibly flat surface, uh, like we're talking using a laser interferometer, you're measuring the flatness of a surface in what's the measurement for wavelength?
Oh man.
We'll say nanometers.
Yeah.
I know you can go down to angstroms, but that's a totally different animal, and we don't play in that realm.
Yeah, we'll take your
But
word for
but
it.
nanometer flatness, right? And so you're going in and you're just scraping just a just fractions of a thousandth of an inch off of the surface. And then you have a precision flat that you use, and you put, instead of Dicam layout fluid, you're using uh, what you'd call high spot. So then you take this precision flat that you have as a reference, put a little bit of the high spot on the surface that you just scraped. And then you bring this precision piece in and you put it in there and you kind of wiggle it back and forth. And then you take that precision piece away, and you can see where all the high and low spots are on there. And then you can take your scraper, your hand scraper, and go in there and knock the high spots down. And once you do that across the whole surface, you you brush all the chips off, the shavings off, and you put your high spot on there again, and then you bring that precision piece back in and set it down, and then wiggle it back and forth so the high spot gets on everything, and then you pull the precision piece away, and you've got more dots. You've got more surface contact with that precision flat. And ideally, for the rule of thumb that I was taught by a couple of different people is you want for a moving way, you want between 18 and 24 dots per inch, per square inch. And that gives you the right kind of surface contact to have a good bearing surface, so you don't get excessive wear in places, that spreads the weight and the force and everything over a good area, but it also makes space for the oil to sit in, so that can still act as the hydrodynamic bearing between the two sliding surfaces.
Well, hopefully, your description of this process can start to paint a picture for folks to understand that when they're buying a machine that has hand scraping, they can
Yep.
understand, okay, now I'm understanding what kind of work went in to make this machine as accurate as it is. And you can understand why
Yep.
things like hand scraping or scraping, I guess it's not always done by hand, but you can understand why it starts to drive the price of
Yep.
equipment up because it's a lot of manual work.
Oh yeah. And there are some great videos on YouTube that show the process of scraping, whether it's scraping for a way for those sliding components, or Matsura has some great videos on there that shows hand scraping, but they're using it for the mounting surfaces.
Yeah, I've
And
seen that.
so like a great example of one is they have the head casting for one of their machines, and they are scraping the ring, the mounting surface where the spindle bolts up to it. But then you flip that casting over and you've got the four mounting pads that the motor sits on. And they use the scraping technique after machining to make sure that the mounting surface for the motor and the ring surface that's the mount for the spindle are parallel to each other and a consistent distance from one another. So that way, when they mount the spindle in and they mount the motor in, that there's no, um, what's the word? Not deviation, but basically, so that way it's a straight line from the motor and or the center line of the motor and the center line of the spindle, so you don't potentially end up having any kind of weird wedging or weird misalignment between the two that could potentially cause a premature failure of either and or both components.
Yeah. So it's not sitting on a crown, so to speak.
Yeah, yeah. And then like the pieces that are mounted that your ball screws are attached to and the bearings that support the ball screws are in, you can scrape those surfaces to bring to again make sure that everything is parallel or perpendicular to whatever surfaces it needs to be parallel and perpendicular to, instead of like some builders where they'll machine it to a certain point and then when they're assembling they'll go, oh, this needs to come up 2 thou, and they'll throw a brass shim or something under there or a mylar shim under it. And I mean, shims work, but given the choice between a machine that uses a lot of shims to get everything right and buying a machine that somebody spent the time to hand scrape and whatever to get everything geometrically accurate and precise, I'll pay the extra money and get the one that's more geometrically accurate because it's going to last longer and it's going to provide better results over the long run.
Let's move on to linear guideways.
Okay.
What is your basic description of a linear guideway?
So a linear guide is, instead of having the big slabs and the big pockets like a boxway does, instead you have a precision ground hardened steel rail that has mounting holes along it that is mounted, and then you have what's called a truck. And that truck has a bunch of recirculating bearings in it, that engage at certain contact points on this precision made rail, and the truck becomes what's called a rolling element on the rail, right? And so some linear rails, they use ball bearings, and then other linear rails use like roller bearings. And the ones that use roller bearings are generally a higher quality and they are more rigid. They are a stiffer design. And so your higher end machines that use linear rails are going to be using the roller type rails, whereas your more economical machines are going to be using the ball type. And then, interestingly enough, inside all these different manufacturers that build these things, these rail systems, they have different grades or classes of them. So you can buy the very best, the very most expensive ones, or they have an economy version of these different rails. And so you and with the price point, you get, the commensurate uh, longevity, rigidity, lifespan, whatever. So, if you're building a not a pick and place machine, but if you're building like some kind of automation in a say a food packaging plant where you don't need to have a real high degree of precision, but you do need to have these moving elements be able to move back and forth for hundreds of thousands or millions of cycles reliably, you can buy the lower grade rails and get what you need for your automation there versus you're building a machine tool that needs to hold 2 micron accuracies. You're going to buy the top end rails that will give you that level of precision.
Is there a dramatic drop off in the amount of weight that machine with linear rails versus boxways can carry?
uh yes and no. And I say it that way because usually when machine builders are saying what the maximum amount of weight that like a mill can handle on the table,
Hmm.
it's not just the motion elements, it's also the motors and the servo drives as well. So for example, uh, we'll compare a VF2 Haas versus a VMX 30 Herco. Okay.
Okay.
So, and the only reason I use these as examples because I'm very familiar with both machines. Or no, not a VMX 30. Let's go with a VM10. So it's similar price point ranges, right? So Haas says, uh, I think on a VF2, I think they say 800 pounds is the biggest or the most weight that you want to put on a VF2 on the table, equally distributed across the table, right?
Hmm.
And they and what they don't tell you, and it's in fine print, is that once you get to about 50% of that weight, like if you go over, I think 300 or 350 pounds, they want you to turn your rapid rates down to 50% or 25%
Hmm.
because the machine is light enough and the motors are sized in such a way that moving 800 pounds that fast, it won't handle it well, right?
Yeah.
So now jump over to Herco, who would say that, okay, we also have an 800-pound weight rating on our table, but Herco, when they rate it for 800 pounds, they are rating it for full rapid speed
Okay.
because they've sized their motors a little differently. They've sized the servo drives differently. They have different components that way. So the weight isn't affected as much by the guideways as much as it's affected by like the motor size and stuff that drives the axis.
And I know some machines, Akuma, like for
Yep.
example, which I'm very familiar with, has servo tuning, so you can
Yes.
actually tune your servos for the weight that's on the table
Yep.
to optimize it, acceleration and deceleration.
Exactly. And a cool thing, I don't know if Okuma does this. I think DMG Mori does it, and I know Makino does it, but like on their horizontals, one of the coolest features that I saw on the Makino horizontals was they had this feature where anytime a pallet was loaded in, and this is especially important when it comes to uh, their big MMC system where you could have dozens and dozens of pallets, right, that could potentially be loaded into that machine. Anytime the pallet gets loaded in before the program runs, you'll see the machine run a little cycle where the tombstone rocks back and forth at a couple of different speeds. And what it's doing is it's basically checking what that moment of inertia is to rotate that pallet and get an idea. I say get an idea, but it's basically measuring to see what its maximum acceleration and deceleration weight or rate is for the weight of that pallet and how the weight is distributed on that pallet.
Yeah.
And it's so they could, because Makino, one of the big things that they really focused on when I worked for the dealer, and that they hammer even on sales presentations, is their acceleration and deceleration rate, because that's where they've been able to shave lots of times out of cycle time in production environments, is how fast the spindle accelerates and decelerates, how fast the axes accelerate and decelerate, and how fast the tool change can do, how fast the machine can do a tool change.
Hmm.
That's where they've been able to shave a lot of time out. And so I think I've seen that Morisiki's can also do that, and I imagine that other companies can as well. But those are just the two off the head that I know of for sure.
Quick pit stop. If you're enjoying the show, hit subscribe and drop a rating. It helps more machinists and makers find us. Tell a friend. Tell your crew. Tell the guy running the second shift. Follow me along on social media at machine underscore tool underscore maniac for thoughts, updates, and some funny memes. We're growing this community with more guests, more value, and more stories that push people to create. So if you've got a niche product getting manufactured or a shop with a cool story, email me at machinetoolmaniac@gmail.com or check out the website machinetoolmaniac.com for merch. All right, back to the episode. Do you have any other points you want to talk about linear guideways before we start moving on?
Um, don't be afraid of. I know some old school machinists, and there's becoming fewer and fewer of these guys in the industry. But don't be afraid of a linear guide machine. Um, I know early on in the life cycle of linear guides, they were not very rigid and they weren't real reliable. And that's just not the case anymore. The technology has advanced to the point where you can get the accuracy, you get the speed, you get the longevity. One of the things I like about linear guide machines is that um, when the machine quote unquote wears out mechanically, it's faster to rebuild that part of the machine. It's faster to replace a set of rails than it is to fully disassemble a machine, take out the turkite. Oh, that's something I forgot to bring up on the boxway machine. So a lot of times, especially on modern machines, you will have something that's called turkite or tersite. I think it's called tersite or something like that. And what that is it's a like a 30 to 40 thousandths thick material that actually glues into the pocket,
Mm-hmm.
and it's usually a polymer type material, and that's what gets scraped. And it also is slippery in and of itself, so it adds to the ease at which those boxways can move against each other. And when you refurbish a boxway machine like that, you end up going and scraping out, getting all of the old turkite out, and then you have to check your mechanical the underlying cast iron or whatever, and make sure it's still square and flat and whatever. And if it's not, you have to surface grind it and do whatever. And then you apply a new layer of turkite and then have to scrape the turkite in order to refurbish it. Whereas on linear rails, it's as simple as you go in, pull back the covers and everything, and then you undo all the bolts and you undo the lube line, and you can pull the whole rail and the trucks out, and you clean the mounting surface where that goes. And then you go and you put the new rail in, and you run the bolts down to where they're snug but not tight, and then you have usually it's an eccentric screw or some kind of a clamp, and then you can go in and run your indicator along the side of it to make sure that it's parallel to the other rail on the other side, and you just torque down these clamps or whatever that straighten the rail out, and then you torque all of your mounting bolts, hook your lube line back up, and you're ready to rock and roll again. So it's kind of a faster rebuild or a faster repair process than the boxway machines are.
That makes absolute sense.
Yep.
One machine tool builder that I think deserves an honorable mention for really successfully using linear guide rails in a lathe format was Hitachi Siki.
Oh yeah.
My
They
dad
were they
had
were
a
kind of the
Hitachi Siki.
pioneers on that.
Yeah, my dad had one, and it was an amazingly well built machine.
Oh yeah. I love those old Hitachis. They are absolute tanks of machines. And Hitachi, what they found is that with the linear guideways, um, that they would have to upsize the rails to maintain a similar amount of static and dynamic rigidity as the boxway machines.
And that's one thing I remember. You looked at the linear rails on the x axis of that machine, and they were
They were beefy.
extremely beefy
Yep.
relative to the
And
size of the machine.
yep. And then the trucks look. I remember the first time I opened up at the first machine shop I worked at, we had a mate or an Okuma horizontal. And I remember the first time I pulled some sheet metal off to do some quarterly cleaning and stuff like that, getting chips cleaned out from under way covers and things. And I remember looking at the rails, and they used beefy rails on the machine. But then I looked at the trucks that everything was mounted to, and it looked like a frickin' shoebox. Like it was huge.
Yeah.
And I realized at that point in time that's like, oh yeah, we're dealing with some substantial mass here, some substantial size. So, and Hitachi Siki was that same way, just built everything big and tough and heavy, and yeah, shoebox sized trucks on those rails. I wanted to hit on one other quick little thing with the ways, and that is Kern machines. And Kerns, they use what's called a hydrostatic way. And what a hydrostatic way is everything that I've been able to read. There's not a lot on it out there on the internet, but from what I've been able to find, a hydrostatic way is basically a box way, but instead of just pumping the oil in between as a lubricant at like 60 or 80 or even 100 psi, they're pumping the oil in between the two moving elements at like 4 or 500 psi. And what they're doing is instead of having, I mean, you still have to have precision flat surfaces and precision rail and stuff, or a precision ways in there, but the machine actually is floating on the oil to the point where you could have several 100 pounds of the head and the spindle motor and everything. But because of the way everything's designed, you can take one finger and just slide it and move it
Hmm.
super easy. And depending on the machine builder, they may not be using ball screws to move it. They might use what's called a linear motor. And so, because you're not spinning a ball screw and you've got that linear motor, and then you're using that hydrostatic way, you can get ridiculous speeds out of a machine. Like think of upwards of 4 to 5,000 inch a minute rapids.
Do you think um, do you think they have a way to reclaim some of that oil that they're
Oh
using?
yeah. Yeah, that oil. So that oil actually, once it comes out from that space, it's low pressure and it just circulates back in and is brought back and filtered and brought back into the hydraulic system. I know Starag has a couple of machines, but they're not little machines like the Kerns are. Like we're talking, I saw an example of a Starag VTL that used hydrostatic ways on the columns for the bridge to move up and down for this turning, this VTL. The table on that VTL was nearly 30 feet in diameter.
Wow.
Yeah, I mean it was an absolute monster. So I know they're used on some of these bigger machines, uh, but but seeing it on a kern and the way that they're using it is really pretty amazing. So anyway, that was just the other thing I wanted to add to the ways discussion.
That makes the perfect segue into our discussion about whey lubrication.
Oh, sweet.
We already talked about it utilizing oil for the
Uh-huh.
hydrostatic, but what are the common forms of whey lubrications that you're likely to see on your machines?
For box ways, it's pretty much exclusively oil. And that's just because that creates that ultra thin bearing surface for those components to move back and forth on.
Is that
It'll
like
the
DTE light? Is that
you'll see either like the DTE light or you'll see Vactra 2 or Vactra 3 used in boxways a lot. Um, so that's that you're not going to see a grease system on boxways. Um, it's oil. Now, when you get into linear rails, you can see either oil or grease systems. Uh, for years, Haas used the Bezier oiler and would use Vactra number 2 as the lubricant. And part of why they used Vactra 2 is because it was what was already being used on the older boxway machines. And so it's like, okay, well, this will work as a lubricant for ball screws and linear guides on this machine. So we'll just use that kind of a situation because it was already in common use. I know Mazak, a lot of the newer Mazaks and Moris and I think Okumas and stuff, they use a grease pump instead to lubricate their linear rails and their ball screws.
what's
Um,
the advantage of grease?
um, so box anybody that's run a boxway machine, especially a boxway lathe, uh, knows that they are slobbery bastards. Like you end up with a lot of whey lube in your coolant consistently because
Okay.
it's just constantly pumping oil in there to keep those ways separated
Hmm.
and so they move smoothly. So that oil has to go somewhere and it ends up making its way to the coolant tank. Um,
Slobbery.
yeah, slobbery. Think of a Saint Bernard. Anybody that's ever watched the movie Beethoven, and the joke is it's just this big slobbery mess of a dog. That's how I see boxway lathes and boxway mills with
Beethoven
their
is
with
a
their.
throwback.
Oh yeah, I'm showing my age a little bit,
I remember Beethoven.
but yeah, just the big slobbery mess is what I think of. And so that can shorten your coolant life and cause really it's not the oil it's not the oil going bad that makes the smell. What happens is that whey oil ends up floating to the top of the coolant and it creates a layer that doesn't allow any kind of oxygen into the or air into the coolant. And so then you get anaerobic bacterial growth in there. And that's what causes that, stinky egg fart kind of smell
Hmm.
with the coolant that so many people are familiar with in machine shops.
Oh yes.
And so that's when skimmers really become a big thing is keeping your coolant oxygenated and getting all of that tramp oil off of the out of the coolant. So then the other lubrication that's used is grease, like I said, and the advantage that has is that It generally doesn't run out. It generally doesn't run out into coolant. Like grease machines, you'll pull back way covers and you'll see where the grease has been kind of flung off onto the bottom side of the way cover, or you'll see it kind of building up in the bottom of the casting or whatever where the ball screw is. But that's as far as it usually goes, unless you've got a wiper leak on your covers, and then the coolant that gets past there kind of washes the grease out. But if you have good wipers and you don't have coolant getting into those areas, you'll just have grease that builds up in there, and that's a lot a lot cleaner and a lot nicer to do. The other advantage that you have is that the grease wants to stick to the grease will leave a little bit more of a film on the ball screw and on like the bearings and stuff inside of the ball screw, to where um it can end up using less grease to lubricate those components than the oil that would be needed to properly lubricate them.
On ball screws,
Hmm.
let's talk about what they do, what they're for, how they're made.
Okay.
What does a ball screw do?
Well, a ball screw is how you take the rotational movement of a motor and turn it into a linear movement of a component. So it's just a big screw and nut assembly. It's just a really precise nut and screw assembly. You can have there's several different types of ball screws. In terms of their quality, you can have rolled ball screws, and then you can have ground ball screws. Those are the two main ways they're made. Rolled ball screws are going to be less expensive, but they're also less accurate. Um, your ground ball screws are going to be a lot more expensive, but those are where you can get really high precision, uh, really high precision screws.
Is a rolled ball screw just like a form tool
Yeah, yeah,
smashes that form into the ball screw?
yep.
Okay.
And when I say precise or precision, like some ball screws, they rolled ball screws, they'll have an accuracy of, plus or minus, say, 3 or 4 thousandths per 12 inches, right?
Hmm.
And so, kind of going back to the example of like the food packing industry and stuff, you don't necessarily need high precision ball screws, but you need that control that the ball screw gives you to be able to move things accurately. And so a rolled ball screw is just fine. Honestly, on lower cost machine tools, um, a rolled ball screw isn't necessarily a bad thing if you have access to laser a laser tracking system like a Renishaw, and you have the ability to put compensation values into the control. Because if you can go, every inch or every 2 inches along that ball screw, and say in the first 2 inches, it's dead on. You tell it move 2 inches and it moves 2 inches. But then in the next 2 inches, you're short by a thou. And then the 2 inches after that, you're like, you go a little more than you go like 2 thou or a thou over or whatever. And you can put those compensations into the control. Yeah, it's not a ultra high precision machine from like Mori or something like that, but it's able to compensate enough that you can still make good parts on the machine.
Do they use rolled ball screws on budget friendly CNC machines?
On some, uh, a lot of the really cheap import machines will use a rolled ball screw. Um, I can't speak on the Haas. I believe those are ground ball screws that they use,
Hmm.
but I think they're a lower grade ground ball screw than some of the other builders.
What do you call the section that rides along the ball screw? What is that called? Is it a carriage?
Rides along the ball screw. So what do you mean? Like the part that actually spins on the ball screw itself?
Yes.
Oh, that's the ball nut.
Okay.
And so that nut, that ball nut, so what that is just like on linear guides have the trucks, a
Hmm.
ball nut has ball bearings inside of it that engage in the grooves of the ball screw, and then they recirculate through the ball nut, right? And that's what allows for the low amount of energy needed to make it move, and that also plays a factor into the precision of that ball screw and how accurately it repeats. And so you can actually end up, so some ball screws, they have a single nut, a single ball nut on there. And so you'll have just a little bit of backlash in there. Well, not really backlash. The preload on the bearings in that are going to be different than on, say, a double. It's like they took two of these ball nuts and have a flange on one end for mounting to the yoke on the bottom of the table or whatever. Um, but then they are able to make an adjustment of the relationship between those two ball nuts to where it preloads the bearings both ways.
So they
So
counteract
they
each
kind of
other.
counteract each other. It pulls tension on the ball nut a little bit, so to speak. And so then you are able to get more repeatable motion out of that ball screw.
That makes sense.
Yep. So um, I believe so. I know Mitsui Seiki, uh, which is a really high-end machine tool. They build milling machines, but they also build grinding machines to grind ball screws. And I believe Okuma does too, don't they? I think
I
Okuma,
know Akuma makes their own ball screws. I don't know if they build the machines that do
I
it.
I think Okuma builds machines to make ball screws.
Wouldn't surprise me.
I think they're one of, there's only a couple of manufacture machine builders that build machines for doing ball nuts or ball screws that are used in their machines. Most every other builder will just go to a company that specializes in making ball screws. So like THK, I think it's THK, NSK, Bosch Rexroth. Um, what the heck is their name? I can see their logo in my mind's eye, but I can't remember their frickin' name. But there's four or five companies. Highwind is another one. They're a Taiwanese maker of ball screws and linear guides. Um, but yeah, there's like four or five companies that really have dialed in the process and make high quality ball screws and linear guides.
Talk to us about backlash. How does backlash show up on your ball screw?
So backlash is you can call it lost motion, and basically what that is it's a mechanical problem to where when the motor reverses or changes direction, it because most machine tool builders are using the encoder on the motor to give feedback for position, the machine thinks that that table already started moving backward or back the other direction. But in reality, that ball screw may have moved just a little teeny bit before the balls in the ball nut have re-engaged and started moving the table physically. And so that's one way you can have backlash.
So it
Um,
typically shows up in a shift in direction on
yeah,
that ball screw. So
yep.
a good way to explain it to the audience, if you're milling
Uh-huh.
a boss
Uh-huh.
and you're making an arc and you hit your peak in the y-axis, and then all of a sudden, so
That ball screw's got to
let's
change
say, yeah,
direction.
you've hit 12 o'clock and now all of a sudden you're changing direction and you're heading down towards 3. You're going to see
A
a
witness
change
mark.
in direction, and that could show up as a witness mark.
Yes.
Hmm.
Yep, you can see that. And those witness marks at 12, 3, 6, and 9 can also be I know Haas they or sorry, those witness marks can also be called reversal spikes. That's what Renishaw calls them on ball bar reports. And what that is how much holding torque the motor is using when it changes direction and how smoothly it's able to make that change. And so it can be mechanical backlash either in the ball screw or in the bearings that support the ball screw actually, or it can be uh, the tuning of the servo motor as well for is what can create those witness marks.
What is the difference between a fixed in ball screw and a floating?
So Fadal, on a couple of the Fadals I've worked on, their Z-axis ball screws were floating, and what that means is that they had, if you looked at them, there's the motor, and then there's a coupling between the motor and the ball screw, and then you have a block that has bearings, usually what are called angular thrust bearing or angular contact bearings, and the stem of the ball screw passes through those, and then that's tightened to a certain amount of preload. And then as you go down to the other end of the ball screw, there's no bearing, no support, no nothing. It's just kind of hanging out there in space. And so that's what a floating end ball screw is. Um, so a floating end ball screw, it's it's easier because it's less expensive. You don't have the additional machine work on that end of the ball screw. You don't have another ball screw mount, and you don't have bearings that are on that end. So it's less expensive that way in terms of components. It's also um, or it's yeah, sorry, it's less expensive because of the lack or the no need of those other components. Um, and in low speed, lower rotational speed of ball screws, um, it's not a big deal. Um, but if you start having to move the machine really fast and you're starting to spin that ball screw fast, that end can actually start to kind of whip around a little bit. And I say whip around, and it's not like it's going to be uh, like the horror videos we see of somebody hanging 4 feet of bar out the back of a lathe and spin the spindle up, and it bends the bar and starts walking the machine across the floor. It's not going to whip like that, but it is enough whip that it can damage the ball nut and cause you some maintenance problems that way.
Mhm.
So then the fixed end, like a fixed end ball screw, usually has another mount, and then depending on the design of the ball screw and the design of the machine, it could be as simple as just having like a deep groove radial bearing in there that just supports the end of the ball screw and keeps it kind of captive.
Mhm.
Or it could be like some of the nicer machines like the Moris, where it'll have another bearing block with angular contact bearings in there, and you'll what's called pre-tensioning, where you put a certain amount of tension on that ball screw and essentially stretch it just a little bit.
What's the
And
advantage of stretching it?
it is, even as you're moving rapidly, it's less likely to induce any kind of vibration or whatever. But when the machine is running for long periods of time and you start to induce heat just from the friction of everything moving back and forth, and as that ball screw warms up, it's not going to act like a jump rope in there. It can expand a little bit, and it takes just a little tension off when that happens, but it's still going to be held solidly, and it's going to be held straight. So that's the big advantage. And then if you want to get into the really nice machines, not only do they pre-tension the ball screws, but then they actually have a hole down through the center of them, and they have the stuff set up to where you can actually circulate uh, cooling oil through the ball screws like you do around the spindle. And so you'll see this on like really nice mold machines and stuff like that, because they're trying because those machines run for such long periods of time, they want to control the amount of heat and thermal growth that happens in the machine over that time to ensure proper accuracy of the parts.
Akuma horizontals have that on there.
They do. Makino does it. I know Kitamura does it on some of their machines. And it's not like we use the term, oh, it's chilled or cooled ball screws. It's not like we're refrigerating the oil and then running it through there at like 40 degrees or whatever. It's usually it's chilled to within a, a couple of degrees of whatever ambient temperature is.
Mhm.
Because you don't want big thermal shifts of parts while or of components while you're running them. You just want them to stay consistent because that's how you get the best results out of the machine is consistency.
So how does the heat that gets in the ball screw, how does that affect the positioning of your machine? You kind of touched on it, but let's elaborate.
Well, going back to what we were talking about earlier on the ball screws, where you can, have you have an accuracy level of the ball screw to where it's, we'll say 1 thou plus or minus 1 thou per 12 inches or per foot of the ball screw, right? So if that's what your accuracy is at, say, 68 degrees, when you heat that up, it changes. It'll cause that ball screw to lengthen out just a little bit, and it might only be a couple thousandths on the ball screw. That when it gets up to temperature, it lengthens out, but it changes where I guess those compensation points would be on the ball screw
Mhm.
because it has stretched out just a little bit. I can hmm, I don't know how to explain that more clearly.
I still remember when I think it was probably the first IMTS I ever went to, and it was a very cool demonstration the effects of ball screws heating up. And this demonstration featured a ball screw with a servo motor and a carriage on it. And this particular setup also had a scale on it.
Uh-huh.
There was a screen above it that had two readouts. One readout was the encoder position, and the other readout was the scale position.
Well, that sounds like a very cool demo.
And there was an infrared camera. So, what would happen is at the beginning of the demo, it would go to a couple points, and you could see that the ball screw was not heated up on the infrared camera. So it would go to these points, and you could see that the encoder reading and the scale reading matched. And then it would sit there rapid back and forth real quick. And you could see in the infrared camera the ball screw was getting warm.
And it was only in that little spot too, I
Well,
imagine,
yeah,
where
it was just going back and forth like crazy.
oh, so it was heating up the whole ball screw.
Yeah, a good chunk of it. I think it
Okay.
was going back and forth like 10 inches or so. So at that point, after it was warm, it would go back to that location and you would see the deviation from the scale because the scale is not impacted by
The ball screw's
the
thermal
ball screw.
change.
Yeah, the ball
No,
screw's
it's
thermal
it's
change.
reading actual movement of the table where
Exactly.
whereas the servo motor is inferring the position because that's where it should be because
Exactly.
of this many encoder counts per revolution and I've gone this many revolutions.
Hmm.
Yeah,
And
that
we're
makes
going to
sense.
cover encoders in the next
When we get
kind of,
into control systems and
yeah,
drives and things
yeah.
like that.
I still think about that demo to this day because it was a great way to show not only the differences between encoders and scales,
Uh-huh.
but also how much heat moving back and forth on a ball screw actually creates because
Oh
it's
yeah,
substantial.
it is. And a lot of that's just because you have to have a certain amount of preload on those bearings to hit accuracy and repeatability on the ball screw. And so what the way you can think of preload is it's got to have a certain amount of pressure on those ball bearings pushing on that ball screw at all times.
Hmm.
And so that's going to create friction.
Yeah.
And we know friction creates heat.
Yes.
Um, Gosh, that demo sounds almost like something that like Heidenhain or Fagor or even like Yaskawa would have shown or demonstrated.
It might have been in the Mori Siki booth. Was
Oh yeah.
right when Mori had purchased Magnascale?
Oh yeah, that makes sense. They
Owns
own
them.
a company that makes scales.
Yeah.
I think Mitsui Seiki also makes their own scales. One of the
Moving
things I
up.
look forward to for IMTS this year is being able to go and check all that stuff out.
Oh man, they got so much. It's overwhelming.
Oh, it is. It's
We're gonna get
very
it all.
overwhelming.